and we'll hit record. There we go. So this is being recorded. It will be on the YouTube channel later. Okay, so the physical sciences are broken down then, mostly into chemistry, physics. You know, I'm not really sure where geology fits. I always thought they were sort of an oddball, but that's just my own prejudice. I hate geology. When we talk about physics, it's really the study of the physical world. So obviously chemistry was all about interactions of matter, measuring matter, how matter interacts with other matter, how matter undergoes change. Here we're talking both about a larger level, a further out level, and a more detailed level. What we will do in the context of a high school physics class is definitely way further out than the kind of atomic view that we had, atomic and molecular view that we had in chemistry. We can break physics down a little bit further. And most of what we're going to do, well, all of what we're going to do, is going to fall really into 3 chunks. Well, possibly a little bit of that. So that first one, mechanics. Mechanics is literally the study of how the physical world interacts. So when we're talking about the motion of objects, be they cars, balls, birds, fish, falling bricks. That's all mechanics. And mechanics has not changed much. This is sometimes called classical mechanics, Newtonian mechanics, named after that real serious genius freak, Newton. He was a very strange individual. We don't even have time to go into how weird he was, but he was. Trust me on this. And basic mechanics has not changed a lot, if any, since its laws were defined. When we want to look at the motion of an object, when we want to look at how a missile travels through air, when we want to look at the effects of air resistance on something, that's all mechanics. Thermodynamics, and by the way, I should say, mechanics is what we'll spend most of the first half of our year on. Lots of motion, two-dimensional, three-dimensional, one-dimensional, two-dimensional, forces, work, that's all under the heading of mechanics. And that's a big chunk of what we do. If you are going on to take physics in college, it is most likely that in your first year, about 1/3 of your physics will be in classical mechanics. About 1/3 will be waves, vibration, optics, and about 1/3 will be electromagnetism. So we try to kind of mirror that here, where we get you a little bit of grounding in each of those. However, we do tend to do more mechanics than anything else, because if you're only going to take one physics class, it's probably going to be mechanics. So that's the one that you're going to end up more proficient in here. Okay, so we got mechanics checked off. Thermodynamics is, what does it sound like to you? Thermodynamics is the study of how heat is transferred within and between systems. So I try to do construction projects in here. My dream in a year where I had unlimited time and we could do everything is I would have you guys build solar water heaters and we do heat transfer, because you can calculate the efficiency of thermal transfer in a system. You can do all this cool stuff. We don't have time for that. And thermodynamics is not something that you're going to get unless you're going onto an engineering program. So we do focus on sort of the basics in here. Vibrations and wave phenomena, you probably had some of this in physical science. If you look at transverse versus longitudinal waves, if you played with slinkies, if you did any of that sort of stuff, that is vibration and wave phenomena. It also starts to edge into the next topic, but sound would be under vibrations and wave phenomena, and a lot of the study of sound. We used to do that. We've cut a lot of that because of changes to the standards. That happens. Optics. Lenses. Did you guys do lenses in physical science? Yeah. Okay, good. We typically do lenses here. I will say that my own experience with the level of optics that's typically done early in your career is that, for me anyway, it's horrible to just be told it works this way. Memorize it. That doesn't work for me. So the nice thing about doing optics at this level is we can do the math to back it up and say, here's the math. If the math says this, it works like this. If the math says that, it works like that. And it all makes a whole lot more sense when you can attach numbers to it. So we should get to the point where we get to calculate image, image size, image magnification, and do some of that. The electromagnetism is something that we will get to. However, it's something that we will have limited time on probably. So this is where we talk about the actual behavior of electrons and their flow. We talk about circuits. We will hopefully do some soldering, and we will construct some circuits. So really, you can see we mostly exist up in this part. Now, all that said, this is the part that's all the cool stuff. I'm sorry. Relativity. There's this weird thing. I'm reading some really interesting, weird, speculative, I don't know if you'd call it science fiction, but in science, we have this really powerful idea that the laws are the same everywhere. That no matter where we go in the universe / multiverse, because it probably is a multiverse, that's what the math points to, that gravity works the same way, attraction between particles works the same way, and, you know, the physical laws of the universe are consistent. This is really important. There is no, 3-meter square area outside Fargo, North Dakota where gravity doesn't work the same way as every place else. That's critical. Because as long as the laws are consistent everywhere and at every scale, so if you have two planetary bodies, they are attracted to one another via the force of universal gravitational attraction. Hey, we have an equation for that. Instead of an app for that, there's an equation for that. We can calculate the degree of force, the actual quantity of the force between them. Mathematically, fantastic. And that exact same law applies to two softballs floating in space. I don't know how the softballs got there, but the law is the same. The equation is the same. Great. There's a hitch, which is that when we get down to the subatomic level, it all stops working. And there seems to maybe be a different set of rules at the subatomic level. This is a problem. Relativity is what attempts to reconcile that issue. This is the weird, crazy thought experiment stuff that Einstein did. I don't know, and this is where I fall off in terms of what I'm capable of even talking about. We're now like out in the deep water, and I got no flotation, folks. I'm not a powerful swimmer. Yeah, we'll talk about string theory. I'll give you some optional stuff you can watch with Brian Greene, Elegant Universe. Relativity is really attempting to understand how it all fits together. So then we get to quantum mechanics. Remember how I said there seem to be two sets of rules? There's how things work at the big, planets and softballs and cars. Well, there's another set of rules that appears to govern how things work at the very, very tiny, and that is quantum mechanics. So quantum mechanics are the mechanics that we see at the subatomic level. Whew, way beyond my pay grade. So far beyond my pay grade, I barely feel qualified to type it on a slide. So really those last two are the ones that are like the cool, interesting, mind-blowing parts of physics. Whoa, did you know? Yeah, well, we're not going to go there, sorry. So it's at the end of your physics book, and when you get to the end of the year and you're doing your big final project, you're welcome to investigate them, but we can't go there here. Hit resume, Moser. The thing that we do is we grossly simplify things for small children, and we proceed to continue to make it more complex as you get older. At some point, it becomes so complex that you quit and go get yourself a large cup of coffee. That's a natural response. It's okay. We have given you the scientific method, and there's even a song right now. There's a show, Ready, Jet, Go, the scientific method. Da-da. We've given you step 1, step 2, step 3, step 4, step 5, return to step 1. Okay. Yeah, okay, sure. Science is really a series of methods, and it's more a way of thinking than anything else. It's about being a little skeptical. Okay, so it's really more about methods than a single path through a way of thinking about things. It's a way of thinking about the world, and the big part is that it's objective and it's factual. Science can't make any claims about anything that is not observable or that evidence of it is observable. So we're always dealing in the realm of the factual and the objective. That's just how we have to work. And we're always seeking to explain phenomena. You've probably heard, well, hypothesis is an educated guess. Oh, thank God. I hate that. And it's okay for 10-year-olds, I guess, but it's not. That's just stupid. A hypothesis is a working explanation. A hypothesis is an explanation of a phenomena. It's telling you how something works. And it's subject to change based on testing, you know that. But it is an explanation of events or phenomena. And subject to testing, it can be revised. So how many of you have heard a lecture at some point about hypothesis versus theory? Okay, good. So we know that theory is something that's fairly robust. That is not something that is taken lightly, like, I got a theory about where I'm going on Friday night. No, you don't. A hypothesis is a working explanation. Once a hypothesis has been subject to repeated testing over a long term, it may be considered a theory. So once a hypothesis has been tested repeatedly, you have results that you can then interpret. And anytime you're going beyond sheer flat numbers, it is subject to interpretation. Numbers are numbers. What the numbers mean is another thing altogether. Once you've got results that you can interpret, you can evaluate what those mean. And that very often happens in the context of other scientists. So that's that discussion piece. Whether it's a peer-reviewed journal, whether it's a conference, whatever else it is. Results are kind of meaningless unless you're discussing them, unless other people are attempting to replicate them. Now, I will put in a quick plug here. It's just our attempts to explain the world. So, when we talk about that piece of having results, having data, having things we can interpret and discuss, what form does that take? Well, it takes a couple of forms. And one of them, okay. Whether we're gathering information to try to build a hypothesis, whether we're testing a hypothesis already, we have to talk a little bit about experimental design, and we're also going to talk a little bit about sort of how information is organized, and especially in physics. So, experimental design, how many of you had something on this in biology? Something about designing experiments. Usually we talk about controlled experiments. The old joke is, did you hear about the biologist who had twins? The first thing she said was, fantastic, I've got a control! But, get it? Because like she could feed one kid all Twinkies and feed the other kid all broccoli, and of course they're genetically identical, so you could see what happened. I got a control! Yeah, okay. So you probably have talked about things like controlled experiments. Those are less frequent in something like physics. We can drop two things and not give one a grease coating and give the other a grease coating, but we're less concerned with controlled experiments here. Very often in physics, we're seeking to explain larger phenomena. And so one thing that comes in a lot is actually what are called models. And who here has built a model with glue and paint and little plastic tabs that you broke off? 2 of you. 3 of you. I'm going to assign you homework. Go to the hobby store, buy a model, snap off all the little tabs, glue carefully, do this in a well-ventilated area. You want to preserve your brain cells. This will tell you how old I am. I built a model of the space shuttle when it was brand new. It was beautiful. I don't know what happened to that model. But anyway, models aren't all physical. So I read a book years ago. It was by a climate scientist who worked at Columbia or something. He was at some prestigious institution, and he had done work on creating one of, at the time, this was probably in the mid-aughts, one of the most robust, most comprehensive, and best thought of climate models. And he said his favorite moment was when an undergraduate came up to him very excited and said, "Oh, Dr. Jones, Can you take me to see the model? No. No. It's not a physical model. It's a bunch of calculations running in a computer. That's the model. It's a mathematical model. If you have graphed something, you have created a model, because when you input this value for x, you get this value for y, therefore allowing you to predict, if we had this value for x, what value of y would we anticipate? That's a mathematical model. Now, most of the models that we're talking about in physics are not that simple. They are not as simple as a two-dimensional plot. They're like, 16-dimensional, metaphorically speaking. They include a lot of factors. They're not straightforward. There are physical models in the world. A globe, which I forgot to bring my globe in from home. A globe is a physical model of the Earth. It's not the actual Earth. Is it missing some stuff? Yeah, it's missing quite a lot of stuff. It's also a lot drier. But it's a physical model nonetheless. We can have verbal models. If you describe a phenomena, that is a verbal model. And you can have visual models. You've probably used a visual model. I used one just the other day when I attempted to help a young man, I think he was a freshman, get to room 151. With this handy dandy, I'm never going to put that in there, visual model that I have of our school. That's a visual model. A map is a visual model. So, models are useful. However, they don't allow us to test a hypothesis. They don't allow us to explain a hypothesis well. Very often, a hypothesis will take the form of a model. Because it's a working explanation. And we can flesh that out into something that shows how the pieces work together. The things that do allow us a little bit more in terms of testing models. Decide experiments and controlled experiments. Controlled experiments, like I said, biologists who had experiments, yes, I got to control. We use those a lot in biology. Controlled experiments are fantastic in biology. They're not, and they're useful in chemistry as well, but they're not as important or useful in physics. They're used a little bit less. They're still used. But when we're talking especially about things that are really big, relativity, or really tiny, quantum mechanics, big ideas, even astrophysics, we get into the realm of thought experiments. These are what Einstein was famous for. And so we're going to flip over and watch a quick video.